Here's a relatively simple way to generate a stable output voltage from a Raspberry Pi using software which is native to the device. So I'm not using any special software to do this. And just to give you a quick example, I just used the echo command to send 2 hexadecimal values to this microchip via a SPI connection. So currently the voltage is about 0.2 volts, and I'll change from FC to, I don't know, FA, and we'll see, push enter, and it drops down just a fraction of a volt. So that's pretty cool. I get sub-millivolt resolution anywhere from 0 volts and 3.3 volts, which is what I'm powering it from. So let's try something a little bit more dramatic. I'll go from FA to AA, push enter, and now you can see it drop down and stabilized around 142.5.6 millivolts. So how am I doing this? Well, I'm using an MCP4921 12-bit digital analog controller, and I pin map these 3 SPI inputs with the SPI outputs available on the Raspberry Pi. So this is the pin header on the Raspberry Pi, which you can see are these pins up here, and it lets me power my chip from the 3.3 volts which is on board. In order to make this more stable, I should probably actually either power it from the 5 volts or utilize this 5 volts with a regulator or a Zener diode to generate a more stable reference voltage so that the output doesn't have the 3.3 volts power supply noise on it. But in any case, it seems to be working well enough for my application right out of the box. So I can power it from this and utilize the ground here. And then the chip select, I connect to either chip enable 0 or chip enable 1. And those differences determine which hardware device it's mapped to. So I could map to multiple chips using these 2 hardware enable pins. The clock matches up with pin 23, and the SPI input matches out with the master out serial input and pin 19. So those are the only connections between the Pi and the chip. I have 1 resistor and a capacitor here just to smooth out the voltage, but I'm not even measuring the voltage on this side of it. This is really just being used so I can easily clamp my voltmeter onto it. So this can truly be done without any passive components, just a single microchip, and I can generate any analog voltage between 0 volts and 3.3 volts with surprising precision. One quick thing that I'll mention, this is about to turn off here. One thing I'll mention is that you control it with 2 bytes. So here you can see that I'm sending 1 hexadecimal value, 30, and then another one, AA. Those are the 2 bytes, and the last 12 bits are the bits that determine the DAC value. The first 4 bits are always control bits, and they're used to set the behavior of the microchip, and they're always 0011, which is 030 in hexadecimal. So if I wanted to crank this up as high as it goes, I would set this last bit to, or the last byte to FF. That would set all of these to 1, but it would leave these 0. So if I push enter and then look over here, that brings me to about 0.2 volts. And 3F is the hexadecimal code for setting all of these to 1. So I'll run that and look at my meter, and I get about 3.3 volts, which is perfect. That's the maximum voltage on my supply anyway. So here you can truly see I'm generating any voltage between 0 volts and 3.3 volts with 12-bit precision using a Raspberry Pi and no software. These are just standard bash commands available on the console. One thing I'll mention is that if I probe this connection with my oscilloscope, which I am doing, you can see there's a whole lot of noise on this line. I mentioned a lot of power supplies noise can get into the reference pin. Right now I'm just connecting my power directly to the voltage reference. So it's working well enough to be able to measure it, but if we were really concerned about the quality of this output, then a Zener diode and some filtering would be of great benefit to smooth out the voltage reference. But in any case, this was pretty easy, and I'm glad it works. Oh yeah, and I almost forgot, just for good measure, I did probe it with my logic analyzer, and I have that information here. Let's see if I can focus on it. This is what it looks like when it's I think I recorded for 1 and 2 seconds, but when I run the command, the chip select goes low for that chip. If you zoom in, you can see the individual clock cycles and the values, 0x33 and 0x78 in this case, and I can turn this into binary if you just want to see what that was specifically. So all of this is working exactly as I would expect.